All right, cool. So, hi, my name is Ratnodeep Bandyopadhyay, and I'm here to talk about HATS, the hardware acceleration toolset for the sigmoid function. Before I start, I would like to give a special thanks to Professor Philip Brisk and Amin Kalanther for providing me with this experience and their help. HATS is a toolset for hardware developers in the field of machine learning. And before I start talking about some of the problems and solutions that are being implemented in HATS, I'd like to discuss why HATS is being created in the first place. So to do that, let's first discuss what machine learning is and why it's important. Machine learning is a compilation of mathematical tools that can be used to analyze data. This analysis can be used to predict the behavior of future data or extract some otherwise obscure information from it. And there are a number of applications of machine learning. For instance, a machine learning algorithm could be given a classification problem like this. Given two photographs of tumor growths, is either photo of a malignant tumor? Or perhaps we'd like the machine learning algorithm to classify a film as good or bad, given data about the film's production, like its budget, cast, director, etc. So from medicine to entertainment, even beyond, machine learning has a major impact on us. And it's at this point, I think it's reasonable to discuss how the sigmoid function is related to machine learning. The sigmoid is an S-shaped function denoted by the Greek character sigma. A unique property of sigmoid is that its input spans from negative infinity to positive infinity. However, its output only spans between 0 and 1. And this is useful in certain problems. For instance, in the first example where the question was, is this a picture of a malignant tumor? If the algorithm is confident that the tumor in the picture is malignant, the output of the function should be closer to 1. But if it's confident that the picture is that the tumor is not malignant, the output should be closer to 0. If the algorithm is not confident about its decision at all, then it'll be closer to 0.5. And this isn't really desirable. So to better increase the confidence and accuracy of the algorithm, it's better to give the algorithm many examples to learn from, but this can take some time. Training a machine learning algorithm on your own standalone machine can take upwards of hours, even days, depending on the size of your dataset and how complex your algorithm is. To counteract this, one solution is to invest in better hardware or offload the grunt work to services like Amazon Workspaces or Microsoft Azure. And while this does improve your training time, the setup and maintenance fees can add up over time. A workaround to both these is designing custom hardware. That way you can train your models at greatly improved speeds, and better yet, you don't need to spend as much money for it. So ideally, you would have your stockpile of data and your machine learning algorithm, also called a model. You'll load your model onto the custom hardware and feed the model your data. It'll do its intended task and spit out some result, whether that be some analysis with the data you fed in or a better trained model. But this is not so easily achieved if you're planning to use sigmoid, and here's why. The sigmoid function is difficult to directly implement in hardware, and this is due to a few reasons. The use of the constant e, which is impossible to represent with a finite number of bits, the use of exponentials, and even division. Collectively, these challenges make the recreation of this function in hardware incredibly expensive or downright impossible without some error. To improvise, there are a couple workarounds, but they can be quite expensive. One solution is to offload the computation of sigmoid onto a separate device, like a computer. Therefore, we're still able to speed up the rest of the sigmoid with custom hardware, just the sigmoid part is slower. But this does throttle the overall performance. And this is where HATS comes in. The goal of HATS is to provide hardware accelerated versions of the sigmoid function that can perform reasonably well. And there are two angles from which to approach this problem from. One is by approximating the sigmoid function with simpler functions, and let's go ahead and take a look at that one first. There are a number of ways to approximate the sigmoid function. One way is to break the sigmoid function into smaller pieces and approximate those smaller pieces with simpler functions. Here we go. This particular approximation is called the ultrafast sigmoid. It's abbreviated as UFS. And you'll notice slight inaccuracies, so let's add the true sigmoid back to compare. While there are deviations, in general, this approximation is quite faithful to the original sigmoid. But upon closer inspection, we'll notice that the UFS function can be further simplified. Here, you'll notice most of the expressions can be simplified to constants or an expression of the form m times x plus b, and these are acceptable. But if you look at the innermost expressions, a division operation is still being performed on them, and we can replace both these expressions to eliminate the use of division entirely. For example, we can replace them with a simple linear function, but this ends up creating a significant error. And we can counteract that by dividing the region into smaller regions and approximating each of them with linear functions. So right now we have 2 inner regions. Let's double this. And you'll notice there's a pretty significant improvement. And we can double it again, and the error went down further. We could continue increasing the number of regions to get a more accurate approximation, but each new region makes the resulting hardware a little more complex. Some machine learning applications may only need 8 regions, so it may prove harmful to further increase the complexity of the hardware. For now, we can leave the number of regions as a parameter the user can set based on their project's requirements. And so this is the resulting function: ultrafast sigmoid piecewise linear, abbreviated as UFSPL. Taking a step back, we can retrace the path taken to arrive at UFSPL. And as mentioned before, this is only one method of simplifying the sigmoid function. There are plenty of other approximations, each offering their own trade-offs between speed, accuracy, and hardware complexity. So far, the discussion has been about making sigmoid faster through the use of simpler approximations. Let's talk about the impact of using a faster numerical representation. There are 2 formats that can be used when trying to represent rational numbers. While we don't need to understand the intricacies of each format, we should understand the benefits and disadvantages between them. Floating point format is commonly used when computing the sigmoid function, and this is because the floating point format offers both incredibly high range and precision. But this benefit comes at the expense of decreased speed and larger hardware. Fixed point format, in contrast, is far faster, and the resulting hardware is considerably smaller. However, it comes at the expense of decreased range and precision. But the sigmoid function doesn't require such a large range, and the precision can be tuned by the user. To explain this, let's take an example. Here's the number pi. It can be broken down into an integer component and a rational component, and these components are separated by a decimal point. Take note of the number of digits each component uses. The integer component uses 1 digit, and the rational component has 5 digits displayed. To represent all of pi, one needs an infinite number of digits. Anything less is only an approximation of its true value. The more digits we add, the closer we get to representing pi. And this is also true when representing numbers in binary. So here's a representation of pi, but in binary. This time with 2 bits in the integer component and 5 bits in the rational component. What's important about fixed point is it can be easily customized by the user. The user can choose how many bits they want in the integer and rational components. So we can generalize the fixed point format with z integer bits and q rational bits. If the user wants a greater range, they increase the value of z. If the user wants a greater precision, they increase the value of q. We can actually see the impact of fixed point format on the sigmoid approximations. Here are some preliminary results. We're going to use the ultrafast sigmoid piecewise linear function as a reference, since we've talked about that before. And we're currently using 8 regions. We're going to vary the number of rational bits and see its impact on the approximation. And this part you're seeing right now is using floating point. Now we're just going to use 1 rational bit in fixed point. Take note of the staircase shape. As more bits are added, more steps are going to appear, and the approximation will better resemble the sigmoid function. So let's go ahead and add 4 more bits of rational precision, and another 2 bits, and another 2 bits. Now it looks just like the UFSPL with 8 regions. It seems like the only source of error is starting to come from the sigmoid approximation we're using. But don't forget, there are plenty of other approximations that can still be used, each offering their own trade-offs between speed, accuracy, and hardware complexity. All graphs above, if not cited, were created using MATLAB. Future models shown in the previous slide will be rendered in MATLAB and then implemented in Chisel, which is responsible for actually creating the hardware. So in summary, the sigmoid function is difficult to recreate in hardware, and existing workarounds can be far too costly in terms of time or hardware resources. HATS aims to provide a set of sigmoid approximations that are fast, customizable, and cheap, with the hope it can optimize the performance of sigmoid computations. Thank you. Are there any questions?
Excellent job. When
you.
you're ready, you can pause the recording and we can jump into questions.